Well, business calculus students, we are on the downhill stretch with Chapter 15. In Chapter 15, we're going to be learning anti-differentiation or integration. I don't know, maybe you're already an anti-derivative type person, right? Because you've worked very hard this semester. But the good news is, if you know the differentiation process, we're simply going to be reversing that process. That's called anti-differentiation or integration. So the rules that you know for derivatives will help you a lot in this chapter. In this video, I'm going to be working through examples 6, 8, 9, 10, and 12. So when you get ready for those, after you've gone through the first part of the notes, join me on the video and we'll work through those examples together. Now, after practicing some of those basic examples, integrating single terms, we have more complicated examples like in example 6. Notice in each of these integrands, now remember the integrand is the part that I'm integrating. So it's between the integral sign and that differential term dx. So in example 6a and b, we have more complicated integrands than what you've done before. So our goal is to first simplify them algebraically and then integrate term by term. We don't want to invent any kind of fancy integration rules. We want to stick with the basic rules that we know. So if you see a quotient like you do on example 6a with a monomial or single term in the denominator, you should split up each term from the numerator over that denominator. Then we're going to simplify with algebra. We know in the bottom we have the square root of x. That's the same thing as x to the 1/2. So in each case, I'm going to rewrite that square root of x as x to the 1/2. Now, in that first term there, we have like bases. When we divide like bases, we subtract the exponents. So if I think exponent 2 minus exponent 1/2, that gives me 1/2 or x to the 3/2. In the second term there, we're simply going to take that x out of the denominator and put it into the numerator by giving it a negative exponent. Now we're ready to integrate term by term. Keep in mind, when I integrate, I drop both the integral sign and the dx. Those are pending operators. They're telling me to do a particular operation to the integrand. Once I actually execute that operation, I drop those operators. So applying our reverse power rule, remember there's the power rule from the derivative. The integral rule is the exact opposite. In a derivative, we multiply by the exponent and we subtract 1 from the original exponent. When we're integrating, we're going to add 1 to the exponent and divide by that new number. So I'm going to take 3/2 and I'm going to add 1 to it. 3/2 plus 2/2 gives me 5/2, and I'm going to divide by that same number. We'll do the same thing with our second term. Negative 1/2 plus 1 is negative 1/2 plus 2/2. We get x to the 1/2 and we divide by 1/2. Now, as you've learned previously, anytime we find an indefinite integral, we always include the possibility of having an arbitrary constant out there. Because remember, if I check by differentiation, the derivative of a constant is 0. So we're always going to account for the possibility that there is a c out there. Now, when dividing by a fraction, that's the same thing as multiplying by its reciprocal. So we can simplify this as 2/5. We're multiplying by 2/5 to represent dividing by 5/2. And if we're dividing by 1/2, that's the same thing as multiplying by 2. And that's simply how we simplify that answer. And there is our antiderivative. Okay? Now, very quickly, to check your answer, anytime you find an antiderivative, you can check it by taking a derivative. So I'm going to use this space for a minute, and then I'll erase it so we'll have space for our next problem. But if I wanted to differentiate my antiderivative, I would apply my rules of differentiation. So I have a constant coefficient 2/5, and then I bring the exponent down in front, and I subtract 1 from the exponent. I'm going to do the same thing for that second term, applying our derivative power rule. And then again, remember the derivative of a constant is 0. So when I simplify this, I get x to the 3/2 plus x to the negative 1/2, which, if you'll remember, looks just like what we had right there when we split up our original integrand. So we got the answer right. The best thing about integration is you can immediately turn around and check it with differentiation, and you'll know whether or not you got the right answer. Okay, let's work on the second one. Now, I can't integrate term by term on this one as it is because I have a function of x being raised to a power. I think if I were to try to differentiate that, I'd have to use the chain rule. Okay, so when I integrate it, I'm going to have to be sensitive to the fact that it's a little more complicated. But we can simplify it algebraically simply by expanding that binomial. So I'm going to think of this as x squared minus 1 times x squared minus 1 dx. When we FOIL this out, we'd end up with x to the fourth. Both the outside and inside terms are minus 1x squared, so they combine to give us minus 2x squared, and then plus 1 dx. Okay, now we can integrate term by term. So again, when we actually find the antiderivative, we drop both the integral sign and the dx. And I'm going to change colors just to show you that something significant happens on this step. So again, the process is to add 1 to the original exponent and divide by that same number. Okay, on the next term we have constant coefficient -2. That's going to filter through to the antiderivative just like it would in the derivative. Then I'm going to add 1 to the exponent and divide by that same number. Next I have 1 whose antiderivative is x. Okay, now where did that come from? Well, think about the derivative of x. The derivative of x is 1, so it stands to reason that the integral of 1 is x. You can also think of that term 1 as 1x to the 0th. So if I integrate that and I add 1 to the exponent and I divide by the same thing, I end up with x. Either way you want to look at it is good. Finally, don't forget we have to add our plus c on the end. It's easy to forget, so train yourself to write that down every time. Now, look at the difference between my two terms. You can express your fractions like this as you want, if you want to, or you can write those as coefficients. Either way is fully acceptable, full credit either way. So this is our anti-differentiation or our integration process. Okay, take some time to work through the notes, learn how to integrate e to the x or e to a multiple of x, and then rejoin me when you get ready for example number 6. Oh, that's the one we just did. Example number, how about 8? Okay? All right, on example number 8, hopefully you've spent some time learning the new formulas. Let me point out to you that we cannot use our power rule. Okay? If I rewrite it as 4x to the -1, and then I attempt to apply the power rule that you've learned previously, if I add 1 to the exponent, I get 0, and we know we cannot divide by 0 in the denominator. So this is a special case. We cannot apply the power rule if we have x to the -1 or if we have x in the denominator. So as you've learned, that's a special formula where we get a natural log. So let's think of this as 4 times 1 over x dx. Now if you want to, the constant is not going to affect the antiderivative, so you can move it in front of your integral sign if you want to. That's totally optional. But the formula for integrating 1 over x leads us to the natural log of the absolute value of x, and then we have plus c. So that is our antiderivative. Now remember, you can check this by differentiation. So fundamentally, you already know this formula, you just learned it in a different direction. If I wanted to differentiate this, I would take my constant multiplier 4, and then when we differentiate a natural log, remember we put the argument in the denominator and the derivative of that argument in the numerator. And of course, the derivative of c is 0. So we would end up with 4 over x, which was our original integrand. So that shows that we have found the correct antiderivative. Let's work on example 8b. Again, we have that 5 over x, that -5 over x term. So I'm going to think of this as -5 times 1 over x, And now we're also going to be working with that e to the negative 2x. So working on just our first term, we are going to filter that constant through to the antiderivative. And then the antiderivative, or the integral of 1 over x, is the natural log of the absolute value of x. Okay? Now, when we integrate an e, it's the opposite of differentiating an e. Remember, when you differentiate an e, you make a copy of it just as it appears, and then you multiply by the derivative of the exponent. Well, if I'm integrating, I'm going to make a copy of the e exactly as it appears, and then divide by the derivative of the exponent. And as always, we'll get a plus c out here. Okay, so I'm going to clean up this notation a little bit. Negative 5 times the natural log of the absolute value of x. Let's call this minus 1/2 e to the negative 2x plus c. Got fewer signs there to read, cleaned up the fraction a little bit, makes it nice and presentable. Okay, now let's double check. Remember, we check our integral by differentiating. So the derivative of negative 5 times natural log of x is negative 5 times 1 over x. Now let's work on our e term. Now remember, we're differentiating. We're going in an opposite direction, so I have to remember which rule to use. When I'm differentiating, of course, the coefficient filters through to the derivative. We make a copy of the e exactly as it appears, and then the chain rule says multiply by the derivative of the exponent, which in this case would be negative 2. And then again, the derivative of that constant c is 0. So when we simplify our derivative, notice over here the 2's cancel, and a negative times a negative gives me a positive. So I end up with the same as my original integrand, which proves that my answer was correct. Okay, so this is a great chapter to really refine your derivative skills. As you're learning your integrals, you can check them with derivatives side by side, and that'll really solidify your knowledge. Let's try an application problem. Example number 9. Suppose a publishing company has found that the marginal cost at a level of production of X thousand books is given by C prime of X equals 50 over square root of X. Remember, that word marginal is fancy for derivative. Okay, so we're looking at the derivative of the total cost function. And that the fixed cost, the cost before the first book can be produced, is $25,000. Find the cost function C of X. So we are going from derivative to original. When we upgrade a derivative to the original function, that means we are applying the integration process. So I need to integrate 50 over the square root of x dx. Before we can integrate, we need to rewrite it as a power of x. So we could rewrite this as 50 times x to the negative 1/2. Remember, square root of x is x to the 1/2. When I take it out of the denominator, I'm simply giving it a negative exponent. Now we're ready to integrate. When we integrate, we transfer the constant to the antiderivative. Then we're going to add 1 to the exponent. Negative 1/2 plus 2 over 2 gives me 1/2. And we divide by that same number. But don't forget, in an indefinite integral, you have a plus c. Now let's simplify this. We have 50 divided by 1/2. 50 divided by 1/2 is the same thing as 50 times the reciprocal 2. So it gives me 100. And you can write it as x to the 1/2 if you want to, or you can go back to your square root notation. So this is my cost function. However, we have this arbitrary unknown constant. So we know sort of what the original cost function looks like, but we don't have all the details just from our integration process. And this is why we call it an indefinite integral. But we have some information. The fixed cost, which is the cost before the first book can be produced, is $25,000. So from that information, we know that if we produce 0 books, we still have to pay our rent, our employees, our electric bill, all that good stuff. So I'm going to use this information and plug it into the cost function that we found by integration, and we'll be able to solve for C. Okay? So C of 0 from my integration process is 100 times the square root of 0 plus C. And we know This is equal to 25,000. And notice here, 100 times the square root of 0 is 0. So we can see that our C must be 25,000. Therefore, our refined cost function, our final answer, is C of x equals 100 square root of x plus 25,000. No ambiguity there. We know exactly what the total cost function is. Okay? Let's try another one. Example 10. Suppose the marginal revenue, remember marginal is code word for derivative, so the derivative of the revenue function, from a product is given by 400 e to the negative 0.1 q plus 8, where q is the number of products produced. Find the revenue function. So we're going from marginal revenue, remember, marginal revenue is the derivative of our revenue, and then we're going to go to total revenue. We need to integrate. So to get R of Q, we need to integrate 400 e to the negative 0.1 q plus 8. And this time we'll put a dq out there just to show that our variable of integration is q. Okay, so let's work on our antiderivative. When we integrate, we always filter that coefficient through to the antiderivative. Now remember, to integrate a power of e, we make a copy of the e exactly as it appears and divide by the derivative of the exponent. Okay, and the integral of 8 is 8q, and we need a plus c out here. Let's clean up our coefficient. We have 400 divided by negative 0.1, or 400 divided by negative 1/10. That's the same thing as 400 times negative 10, so we get negative 4,000 e to the negative 0.1 q plus 8q plus c. Now, the only thing that we don't know at this point, of course, is that arbitrary constant. We need to solve for it so we have our actual revenue function. Now, if we produce 0 books, that means our revenue would also be 0. So I'm going to plug in 0 for Q, and I'm going to set my revenue equal to 0. That should allow me to find C. So if R of Q equals 0, and we can plug in 0 for Q, this is an equation that we can use to solve for C. Okay, so 8 times 0 is 0. That term's going to go away. Notice right here we have e to the 0th power. That's equal to 1. So we have 0 equals negative 4,000 plus c. And if I solve that for c, we determine c is equal to 4,000. So I can go back up to my revenue function, my R of Q, and refine it and make it specific. We have negative 4,000 e to the negative 0.1 q plus 8q. Plus now we know C is 4,000. So we have obtained our total revenue function from the derivative. Remember previously I gave you the total revenue function and asked you to find the marginal revenue. We just differentiated that. Okay, part B, find the demand function for this product. Recall that revenue is equal to quantity times price. And that price is describing the demand in terms of quantity. So if I want to get the demand out of this, I can simply divide both sides by Q. So dividing both sides by Q, we have our demand function. So to find our demand function in terms of quantity Q, we need to take revenue divided by Q. So we found our revenue function. Let's call this P of Q. That's going to be R of Q divided by Q. So our demand function is revenue, negative 4,000 e to the negative 0.1 q plus 8q plus 4,000, and we divide that whole thing by Q. There's our demand function. Okay, we're going to skip example 11 from the book. It has to do with physics, and our focus is business. So let's go ahead and move on to example 12. Find a function f whose graph has slope f prime of x equals 6x squared plus 4 and goes through the point 1, 1. Remember, f prime is a formula for finding the slope of the function. Well, let's see what we have here. We have f prime and we need to find f. To go from f prime to f, we need to integrate. So the function that we're looking for is going to be the integral of f prime of x with respect to x. F prime of x is given to be 6x squared plus 4. We're going to integrate term by term with respect to x. So we're doing the exact opposite of what we do when we differentiate. So we're going to add 1 to the exponent and divide by that number. And when we integrate 4 with respect to x, we gain an x. And we always have this arbitrary constant out here. Let's reduce. Our function f of x that we're looking for will have the form 2x cubed plus 4x plus some constant c. So we've got a form of the function that we're looking for, but it's not yet specific. It's indefinite because of that arbitrary constant c. But I can use this information to find out what c should be. We know from that ordered pair that when we plug 1 in for x, we get 1 out for y. So we're going to set our function equal to 1, and we're going to plug 1 in for x. And we can use this to find c. So remember, we set it equal to 1, and we plug 1 in for x, just evaluating that ordered pair there. So let's see what we end up with. Subtract 6 from both sides. Looks like c should be negative 5. So the function that we found over here, we can refine and say f of x is 2x cubed plus 4x minus 5. You could graph it and verify that it passes through the point 1, 1. You could find a derivative. In fact, let's do that. If I check this answer by differentiation, the derivative would be 2 times 3x squared plus 4, or 6x squared plus 4, which matches the original given derivative. All right, I hope this video was helpful. Thank you for taking the time to watch and to listen. As always, you can contact me by email if you have any questions.